If you study mathematics at school, you need to watch this video. And I'm very confident that it will have something new for you, even if you're a teacher. But certainly, if you're struggling with finding areas in high school, or even whether you're quite accomplished at the feat, whether you're in senior high school, or even a freshman or a beginner at high school, this video is for you, and also the ones that follow. In all these videos, finding areas is one underlying concept, and this is it. That when we want to find the area of a surface, or the area within some figure, we do so by comparing it with some standard area. Now, we could have chosen a circle, or a triangle, or a square, or some other shape. We prefer one that tessellates, that is, that it fits together without any gaps. In fact, it must satisfy this condition. And because the circle does leave gaps, it's out of contention. It turns out that we prefer using squares because they stack well, they're easy to count. So if we have a shape, particularly a regular one, that's divided up into squares, if we can count the number of rows, 3 rows, and 1, 2, 3, 4, 5 columns of squares, we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, or as you're taught in primary school and early high school, simply multiplying this number 3 by the number 5 tells us the number of squares inside the shape. It's a very simple method, and it's based on this rather than some other shape. So we measure areas in square units. Now that's the underlying concept, that we measure in square units, and a fast way of calculating within a rectangle is to multiply the number of rows by the number of columns, or this length by this length. Now, to summarise the formula, we would write area equals, we can call it length 1 by length 2. A lot of textbooks will call it length times breadth. Some textbooks will write length times width. Others will write base times height, because when a rectangle is sitting in this orientation, this is the base of the rectangle and this is the height. So that's quite a popular formula as well. The fact is that whatever letters are used, there are going to be 2 letters multiplied together, because there are 2 lengths multiplied together. Because there's such diversity worldwide, there's no set agreement on this, and I have my own preference. I'm going to share it with you. I don't like this particular formula simply because it includes a height. Now technically, yes, that is the height of the rectangle, but later when we need to use this formula to find volumes of prisms and pyramids, and when we use it with the Trapezoidal Rule and Simpson's rule for approximating areas under curves in senior high school, we use height to represent other things. And I don't like equations having 2 heights in them. So therefore I avoid this formula. I actually encourage my students to use this one. Length times breadth. If you really insist, you can use this, but for these videos I'm going to be using this particular formula. And the units, of course, will be square units, because worldwide we use these as the basis of finding all areas, because they stack well and they're easy to count. This is the basic concept of finding areas. Now I'm going to show you how we build from that to understand how to find the areas of a variety of simple plane shapes. So let's clear the board and have a look. So let's look at our summary. The basic shapes we find areas of are these 3. The square, the rectangle, and this one, which, because these 2 sides are parallel and these are parallel, we call a parallelogram, or parallelogram. Most textbooks that I've seen have a formula for the area of the square. Area equals s squared. That is the side times the side, this side times this side. Perfectly legitimate. It just happens to be very confusing to students. This one in a lot of textbooks is base times height. And this one in a lot of textbooks is also base times height. I've seen some textbooks that have replaced this one with length times breadth, so they've managed with three simple and essentially identical problems to create three separate formulae. The reason the same formula is used for the parallelogram is that if this is the base, if this length here is the base of the parallelogram and this perpendicular height is the height of it, then removing the triangle from this end and taking it to this end converts it into a rectangle of the same base and the same height, or the same length and breadth. Actually, I'll leave those red marks there for you. What I wish to share and what I teach my students to do is simply for these three equations to write area is length times breadth. And I refer to these as rectangles, or like rectangles. They're not exactly rectangles, but they're like rectangles. The next three shapes are these ones: a triangle, a kite, and because I'm not working on a long page, I'm going to work over here, a rhombus. Now, how do we work out the area of these? If I call this the length and this the breadth at right angles of the rectangle, of the triangle, if I call this the length and breadth of the kite, meeting at right angles, and the length and the breadth of the rhombus, again meeting at right angles, I want you to see what happens when I draw a rectangle around these shapes. Here's a rectangle drawn around the triangle. Now, this height here divides the rectangle into two, one here and one here. This rectangle, how much am I shading? I think you can see that I'm shading half that rectangle. The rectangle on this side, how much am I shading? I think you can see I'm shading half. So how much have I shaded out of the entire rectangle? The answer is half of it. A triangle has an area half that of the rectangle that surrounds it. Have a close look at your kite. Draw a rectangle around your kite. Look very closely at the rectangle in the top left-hand corner and shade half the rectangle because there's a diagonal line there. The one here, shade half. The rectangle in the bottom corner, shade half. The rectangle in the top corner, shade half. A kite is half a rectangle. Draw a rectangle around the rhombus. The rectangle has the same length as the rhombus and the same breadth, just as it had same length and breadth as the other shapes. And again, you can see that in each quarter, half of the shape is going to be shaded in that quarter as well. Consequently, all these three shapes are half rectangles in area. So, to summarise that, I write this: area is length times breadth divided by 2. And my summary is to call them half rectangles. I have seen school textbooks use half base times height, half x times y, or half a times b, and also half x times y or half a times b. And students get very confused about the variety. The essential simplicity of it is that these three are already rectangles or can be made into rectangles, and these three are half rectangles. So instead of having 4 or 5 or 6 different equations, we have 2, and the 2 are very strongly related. And this makes it very much simpler to remember. We're not finished the entire story yet, and because I'm running out of board, I'm going to shrink this little summary down a bit before we add the last 2 items. Next shape, how do we find the area of a trapezium? Where this side is parallel with this, again we have a length and a breadth, but the length on the other side is different, so we'll call this a length as well. I'll call them L1 and L2. Might be fun for those of you brought up on bananas and pyjamas, but still, length 1, length 2 and the breadth. Now different textbooks will call out the height, an A and B, or the height and other letters for the sides, but this will do us. How do we find its area? Well, we can't simply chop this triangle off, as we might have with the parallelogram, and taken it to the other end and fitted it in, because this triangle will not fit here because the angles are all wrong. So that isn't allowed to us anymore. There are a few ways of explaining this, but what one smart person did was they said, what if we find the halfway mark? So this length equals this one, and we chop off this triangle. Where could we put it? Well, we don't have to take it to the other end. We can swing it up here and fit it in here because the angle is exactly right. And if this length equals this, it will fit in there exactly and make this end just like the end of a rectangle. Guess what? We can go to the other end and find the halfway mark and cut off this right angle triangle here and swing it up into the gap here and square that end off. And we've succeeded in converting a trapezium into a rectangle. By cutting the 2 triangles and swinging them up, there it is. Now I think you can see that the breadth of the trapezium is exactly the same as the breadth of the rectangle. It hasn't changed at all. What has become a problem for us is to know exactly how long this rectangle is from this point here to this point here. Well, that's an interesting question. The fact is that there's a theorem in geometry that we can appeal to. It's quite a nice little theorem, and it says this. If we have 3 parallel lines equally spaced, and 2 transversals are drawn, not only does it say that this must equal this, and I think you can see the similarity in the pattern here, and that this must equal this, it also says that this length must be exactly halfway between this length and this one. To give you an example of what I mean by halfway, if this is obviously not to scale, but if this was 6 and this was 10, what number is halfway between 6 and 10? I think you know it's 8. Let's change the numbers. Excuse me for the black smudges. If this was 10 and this was 20, what number would belong? Well, I think you'll agree it's 15. That's exactly the number we need for the length of the rectangle. That's all well and good if they're simple numbers like that. But what if I chose numbers like 17 and 83? Or 54.2 and 17.1? Or numbers using fractions or even more complex decimals? We need a method to find this middle length that doesn't just rely on our understanding of numbers, our natural understanding of numbers. How do you find the length that's halfway between two other lengths, or the number between two other numbers? Exactly between, in the middle. Well, you've been doing that since you were in primary school. You might not realise it, but your teacher does that every time you sit for an examination, and your teacher will get the results for the class. And if they want to know where the middle of the class is, I think you realise they add all the marks up and pretend that they share them equally around the class. So they divide equally by the number of class members. So if there are 20 in your class, they'll add the 20 marks up and divide by 20. If you're in a class of 2, they'll add your marks together and divide by 2. And that's exactly what we do here. We add this length and this length. So here we do 17 plus 83, and we would divide that answer by 2. Now I think you realise I was a bit sly and I chose two numbers that add up to quite a nice number. 17 plus 83, or 83 plus 17 makes 100, and half of 100 is 50. So this in fact would have been quite an easy dimension to use for finding the area of the rectangle. Multiplying by 50 is quite easy. But there's our pattern. So if we have a rectangle with a length 1 and a length 2, what's the length in the middle? I think you've worked out we call this an average. The average length, or the middle length, is L1 plus L2 divided by 2. And that means the area of a trapezium is length 1 plus length 2 divided by 2. That's the length of the rectangle multiplied by the breadth. So here we have areas of rectangles are length times breadth. Areas of half rectangles, like triangles, kites and rhombuses, are half length times breadth. And the area of a trapezium is the average length times the breadth. Well, I hope you find that a lot simpler, but we're not finished. I'm going to summarise this over here and then look at our last shape. So please keep watching. We have just one shape remaining, and that's this one. How do we find the area of a circle? Well, believe it or not, we convert it into a rectangle, just like we compared these shapes with a rectangle and even converted our trapezium into a form of rectangle. Now, how do we manage that? Well, before I do it, I want to discuss the parts of a circle. The length right across the middle we call the diameter. The word diameter means to measure across the circle, and half of the diameter we call the radius. So I'll put a little arrow here and call it radius. It's a very important measurement. By the way, you have a bone in your body called a radius. It's the big arm in the forearm, the big bone rather, that leads up towards the thumb. The ulna is the small one here, but radius. And I just think of it in terms of martial arts. When one does a block in martial arts, the radius is the one that rotates around the elbow, a bit like in a circle, and performs the block. There's our radius. The distance around the outside of a circle is called its circumference. And how do we work out the length of the circumference of a circle? Well, by definition, and this is for another video, the circumference of a circle is pi times the diameter. Pi is just, don't think of it as a weird number, it's just a number around 3. So if I'm at someone's house and they've got a swimming pool that's circular and say it's 4 metres across, I think 4 times 3, 12, it's a little bit more than 12 metres around. Very, very simple. If I see a track that's 100 metres across, then I know it's a little bit more than 300 metres around. That's all this is for. And because the diameter right across is 2 radii, I can write this as pi times 2 radii, which is 2 pi r. Now, this is for a discussion in another video, but I just need to use this information. What we do to a circle is to convert it into a rectangle is we cut it in half. And we take the top half, for example. Here it is. There's the centre of the circle, and we get a pair of scissors and we cut very, very, very thin slices or sectors from the centre out. And we stop just a minuscule distance before we cut through the paper. Now, I've actually done this and I encourage you to try it, but lots and lots and lots of little cuts. So far so good. You then grab each end of this shape and you pull it tight, and what you end up with, I think you'll see, is a shape that looks a bit like this. A fairly straight line, and admittedly will have tiny, tiny bumps in it. And hanging all the way along it will be these little wedges. All the way. They're all the same length because they're all going the same distance into the centre of the circle. So these wedges work all the way across. I'll try and draw them all in quickly. All the way across there. Now, if that's the top half of the circle, if we took the bottom half and cut it up the same way and opened it out and pushed it up, all the little wedges would fit in between these ones if there were the same number of wedges in each half. And it would just slot in there very nicely and make, you guessed it, an almost perfect rectangle. Now, I'm not going to quibble at this stage. There's a great discussion about this, but I want to look at two features of this rectangle. What's this distance here? Well, that was the length of each of these wedges, wasn't it? And then what was the length of the wedge? It was the distance from the outside into the centre of the circle, which is the radius. How long is our rectangle? Well, it's the length around half the circle, because we straightened it out to get this. Now, what is the length around half the circle? Well, the distance around the whole circle is that. This is 3 different ways of writing it. So the distance around half the circle is half of 2 pi r. And what's half of 2 pi r? It's 1 pi r. So that is pi times r. So we've been able, with some very skillful cutting and a little bit of make-believe, we've been able, or a bit of imagination more to the point, we've been able to convert our circle into 2 halves and then into a pretty decent rectangle. What's the area of this rectangle? Well, the area is length times breadth, and the length is pi r and the breadth is r, so it's pi r times r, which is pi r squared. So the last part of our summary is the area of a circle is pi times the radius squared. Notice, by the way, that the length and the breadth always had to be at right angles to each other. Length and the breadth at right angles. Length and the breadth at right angles. Length and breadth at right angles. Length, breadth at right angles. And it means that essentially we're multiplying this radius times this radius, r times r, and we'll need just over 3 of these squares, if we imagine a square out here, to make up the area inside a circle. So pi r squared is how we find the area of any circle.